great pleasure. Okay. It's my great pleasure to introduce Simon Arridge from University College London. Simon is a great expert in inverse problems, internationally very much respected, and has done some really pioneering work, for instance, in photoacoustic tomography, but in general in imaging methodologies, inverse problems methodologies related to medical physics type of problems. And in the last, I don't know, couple of years, 2, 3, 4 years, has really gone into exploring the potential of deep learning solutions for solving inverse problems. And on the other hand, understanding deep neural networks better with some of the things that we have been developing in the image processing world. And that is, I believe, what he's going to talk about today, in fact, is on learned solvers for forward and backward image flow schemes. And yeah, I really look forward to your talk, Simon.
Okay, well, thank you.
This talk is being recorded, so if you don't want to appear in the video, please switch off your own video.
Okay, great. Thank you, Carola, for the kind introduction. And thank you, everyone who turned up. And apologies, this moved from the regular Tuesday morning slot, which I can't make. So thanks for coming, especially today, which is out of the regular schedule. Great. So, I'm sorry. So yeah, let's talk on learned solvers forward and backward image flow schemes, and many people to thank over the years. But in this talk, I'm mainly talking about work done with these three co-authors. Faculty member at University of Ulu and part-time appointment at UCL. And I won't mind, there was finally a student just completed his degree. So here's the outline of the talk. And so I'm going to be talking to a large extent about diffusive processes, nonlinear and nanostructured diffusion and imaging, but we also have extended some of these concepts to a few other flow schemes, which I'll come to. Okay, so let's begin. So in general, talking about how deep learning can be used in inverse problems. So the general definition would be, can we find a, oh, sorry. I need to talk into the mic, apologies. So if we are concerned with, let's say, a forward problem here, we want to say that we have a mapping from spaces X, Y, and in general, we would set that up through physical principles, but we want to include the possibility of that being defined by a parametric mapping where the parameters may be learned. And so, generally speaking, and many of us are interested in this idea of how can learned models replace physical models? Should they completely replace them at one extreme, or be completely ignored at another extreme, or how can they be combined? And this is intimately caught up with the question of what there's some chat about. Okay. What are appropriate architectures for learned model, and what? How many? And there's quite a lot of work in this area. Just a few to mention here. Some work from 2015 by Chen Yu and Pok on learning optimized reaction diffusion processes. Many of us know the pioneering work of Wayne and Yi on machine learning via dynamical systems. Rudodo and Haber, that Haber will be speaking later today, have done much interesting work on the connection between neural net architecture, particularly ResNet architectures and PDEs. Their relationship to optimal controls being explored, for example, by Benning et al. And lately, much very interesting approaches looking at the infinite dimensional cases of Fourier neural operators from Andrew Stewart and his co-workers at Caltech. Which provide, all of these have the common theme of designing networks based on PDEs. To some extent, the filters are localized because of convolution, like, although of course that can include multi-scale aspects as well. But what we were thinking about was designing global spatially varying filters, taking nonlinear diffusion as a starting point. A couple other things that are important to mention. So one of the interesting works in this area by a group of Dong in Beijing, PDEnet, which looks at learning PDEs of a general form where the time derivative of a field depends on a function of the spatial derivative. So this general form covers quite a lot of known PDEs. And their aim is to design a feed-forward network that approximates PDEs from a solution of samples over time. So you have observations of a state as a function of space and time, and then learn an appropriate PDE that describes that. And the key components there are this idea of a block which contains spatial derivatives, and then a symbolic combination of spatial derivatives, multiplicative, and two powers that can be combined to produce many of the equations that we know in mathematical physics. Example of that, we applied this to the problem, just anticipating the problem we're talking about. That's the idea how it works. This top line here shows an anisotropic diffusion. You could possibly see that there is a spatial blurring going on there, which is preserving edges of the principal features and blurring within low noise regions or texture regions. And then PDE, you apply this, you hand this to PDEnet, and it gives you back an expression in terms of the derivatives up to an order you can specify. So when we applied this to this anisotropic model, it tries to produce a proxy for that in terms of constant multipliers of spatial derivatives up to a specific order. And visually, it looks approximately correct. Of course, the effect of the division is not very strong here, but basically it's producing a global approximation. So there's no spatial variation. Yeah, so this bottom line is the model derived from that global element, or even of each component. But in a way, it's not very, I mean, it's quantitatively doing a good job. And also, I mean, it's not really to be expected that you can approximate a spatial varying with global coefficients. Another interesting approach is the group meta-learning set of differential operators, and here the idea is to try to solve the Green's function. So you want to learn the inverse mapping, the Green's operator, which depends on parameters, the physical parameters of the PDE. And the problem is that this would be a huge dense matrix, stored, and questions arise: how do we represent the output from arbitrary parameters, and how should we represent the training data? And among other ideas, there is something that looks akin to a encoder-decoder style representation, where you have a redundant form of wavelet transform and its inversion, and then the learned components are representing a compressed form of the coefficients of those basis functions that represent the Green's operator. And then the second idea is to use training data, which is sets of samples which are varied both over the source of the operator, initial position, and the parameters. And that's been applied to numerous general inverse problems in scattering. In this setting, it's linear. But in PDE, that's not. Okay, so let's talk about some of the work that we're doing. So we were actually really, again, we were motivated by thinking of nonlinear inverse problems and what would be a sufficiently challenging but not too strongly opposed inverse problem. And we decided that one would be an anisotropic diffusion process, which we define here as PDE, which is the time variation of a spatially varying, well, possibly spatially temporally varying diffusion coefficients with initial conditions. So the forward mapping in this case is the mapping from the initial conditions to the final state. So we represent this PDE operator as simply S by L of gamma. And in the isotropic case, things are fairly easy to analyze because this is just the spatial Laplacian, and we do have a Green's operator here, but the kernel being the Gaussian. And so it's well known that the diffusion process over a time t leads to spatial blurring with a variance of 2t. And so if you're evolving with an initial condition of an image and evolving this over time, just leads to a spatially homogeneous blurred image. But we're interested in the nonlinear case, so we'll say there's a scalar diffusivity, which we'll put in the interval 0, 1. And one of the prototypical examples is the Rhodomanic filter. There's a number of variations of that, but it's a convenient one where you make this diffusivity the reciprocal of 1 plus the square of the gradient of the image with a threshold controlling the effect of the magnitude of the image. And what this essentially means is that if the magnitude of the image gradient is large, as opposed to 0, which means that there's no spatial blurring. And as we go into very small edges, this goes to 1. So this varies between Gaussian blurring and large image blurring. And so if you program this in Evolver, you see these quite powerful so-called anisotropic diffusion schemes. There are many, many others, but this is just a well-known example. And this has this property, sometimes called edge-preserving flow. And the idea is that the texture here is being blurred out faster than the strong features of the image, such as the tripod edges of the figure. But as you proceed for longer and longer times, eventually all of the features are eventually blurred, and the end state is just once again a uniform image, or that could be a piecewise constant image. So there's no general solution for that. So we have to proceed numerically. And then we just proceed formally. We say that between two time states of the function f, we can say that the increments from the integral of the separator over time, and then we make the approximation that in this time interval it's constant. So we fix gamma at time n, the mean or a sample point in that time interval. And so we just say that the increment is given by delta t times second order derivative. So this means that we can solve this just by a iterative sequence. So we can use an explicit scheme or an implicit scheme, and we know that the explicit scheme satisfy the CFL conditions, whereas the implicit scheme is unconditionally stable. But in terms of accuracy, it depends on taking small steps. Within the limit as delta t goes to 0, either of these schemes will solve the problem. So now we consider this mapping from the initial state to the final state as the concatenation of a sequence of these incremental steps. All right, so this now begins to give a clue where we're going, because this now looks like layer operators from the initial state to the final state. Before we look at that implementation, now we look at the inverse problem. So again, for the isotropic case, the problem is stationary convolution, so the inverse problem is stationary deconvolution. And of course, we know it's unstable, but just to reiterate why that occurs, if we were in the Fourier domain, because we have stationary convolution, it's a multiplication in the Fourier domain. And so the time evolution is given by the product of the Fourier transform of the initial state and the Fourier transform of the kernel, which is itself a Gauss. So the inverse could formally be done by division. We just multiply by this exponentially growing function. But of course, this is unbounded, and so there's no spatial convolution filter which corresponds to this unbounded operator. And of course, it's also unstable even in the presence of a small amount of additive. And so we have to regularize. But let's just proceed formally with that idea. So if we were to take the Taylor approximation of this operator in the Fourier space, and we just make some discretization in time, so we say that the final time step is the product of intervals delta t, then formally we can say that this inverse operator is the product of these incremental operators. And as delta t becomes small enough by Taylor series, we would expand this, remove the higher order terms, and we see that converting back to the spatial domain, this just corresponds to an incremental operator where we now take the delta t times the negative delta t of the Laplacian. So we could call this the Green's operator for the incremental step. And this also corresponds with the inverse of the implicit update, because the implicit update was given by putting on the left-hand side the density minus the Laplacian and inverting. So to go to the inverse, we just take the explicit form of the implicit, sorry, we take the exact form of the implicit update operator. And this then lets us suggest that we could invert this process by concatenating these incremental operators. Now, of course, we know it's unstable because the addition of any noise will be exponentially growing. Nevertheless, we could write this down as a formal incremental state, and we could say system, we could say that that's what the limit as delta t goes to 0. This would solve the inverse problem. So now we're going to conjecture that we could write down for the non-stationary case a set of local non-stationary filters, zeta, which would have this same local form, so incremental form in time. And the key thing is those filters will only have local support. And for the non-stationary case, the concatenation of these filters will solve the inverse problem. And just as a remark, there's a classical process in image correction, image analysis called unsharp masking, which is normally written in the following way, that we say that the observed data is given by a small multiple of the difference between the observed data and a Gaussian smooth version for some Gaussian scale and some sufficiently small epsilon. And if by following that through in the Fourier domain, we would say that the unsharp masking is achieved by taking, by subtracting the plastic of an image. And sometimes that's done by analog methods as a simple way of sharpening the image. So what we're potentially doing is replacing the stationary filter by a non-stationary filter as a kind of unsharp masking, and then concatenating these filters to provide the inverse over the whole diffusion scheme. All right, so how does that translate to a network idea? So we go back to this explicit time stepping scheme, and then we reformulate this as a network by interpreting each element's layer, Fn for the sample of the image time Tn. And we'll use this idea of a diffusion layer operator with learnable parameters, gamma, and we'll include the time step. So we write this layer operator d theta on the layer parameters Fn as this identity, like a resonate style, with a time step and a learned diffusion curve. So for two-dimensional images, this amounts to learning the components of a sparse operator. So we write this LDT in its numerical form as weights on the diagonals, on these off-diagonal terms, and the central diagonal, the leading diagonal, is a negative sum over the off. This satisfies the property of the diffusion equation because the so have a null space of any constant function. And so this just translates to this resonate style architecture where we take this learned coefficients of the off-diagonal operators, increment at each time step, and add the identity to it. So this would be for isotropic diffusion. We would just write these down. But now for nonlinear diffusion, the filters depend on F itself. So we can't learn them explicitly. So we now introduce the idea of an implicit estimator. So now we're going to say that based on the current state, the current layer values, we're going to write a neural network which learns the diagonal components of this diffusion operator. So what we use is a small convolution neural network applied to the image in the filtering. And then when we want to do inversion, we can just run this process backwards, but we know that we need to include regularization. So we're going to assume that we are going to add a smoothing operator to this incremental backward diffusion step, which we'll write in terms of this generalized matrix W. So now this actually, sorry, I should correct that. So now this has this extra component on the diagonal. So now the learned diffusion, nonlinear diffusion looks like this. So we have this. This is where this is the trainable part of the network, where we're learning a neural network which learns the components of this filter. The filter is specified explicitly in terms of the diffusion equation. Right. So given the layer Fn, the filters are explicitly estimated by a small CNN, and then applied in this explicit way. We're essentially learning the diagonal components. And here now we see in the unregularized state, we only learn 4 of them, and the 5th one is negative sum on the diagram. But in the regularized version, we remove this mean free condition, allow that to learn regularization as well. So I'll show results with both of those approaches. Okay, so let's look at some computational results for that. So we first of all just do a simple deconvolution experiment. So we just apply this to an isotropic deconvolution. So we set the diffusivity to constant. So starting with the disk here, Gaussian kernel convolution image. We're learning the forward problem. So in the Fourier space, this is like a Bessel function. The Gaussian is just also a kernel. Sorry, the Fourier transform of the kernel is also Gaussian with the reciprocal of the variance. Taking the product of those two, we get the convolved image. And the network output is correctly learning this process. Just looking at it in a bit more detail, starting with the initial image. We have the network which learns the weights and learns this Laplacian-like filter. We add the image and we get the next iteration. Here's the corresponding coefficients learned in Fourier space. So as we proceed in the network, we're learning more and more higher frequencies in this convolution kernel. We get to the final step here. And then we apply a final ReLU to enforce positivity. Now, the interesting part then comes when we want to apply this to nonlinear problems. We then look at the pro-pneumatic function, which we repeat here. And we are going to concentrate on this inverse problem of restoring an image that's been contaminated by noise. So we use this STL10 database, training test, 10 times test. So this is some examples from that, and these are the results of just running a pro-pneumatic anisotropic diffusion that has this characteristic edge-preserving form where some of the texture is blurred out, but the edges are preserved. And we add noise, and then we use Sticknet to invert. And you can see that it's qualitatively doing a good job. So here's the original reconstructed and the residual, and here we compare with a standard UNet architecture. Doing the same job of taking the pairs of the original and the diffused image and training a UNet to invert it. And of course, they look qualitatively very similar. So the question is, what differences can we see? Sorry, that's no noise here with 1% noise. So what is the difference here? So updates in internet are explicitly, and we're only learning, we're only using training and learning to produce these filters. And then we can be somewhat flexible in how we impose constraints on the filters and on the differential operators. So this is making use of our understanding of the problem we're addressing as opposed to purely data-driven process. Then there's quite a difference in the learnable parameters. 5-layer DeathNet has 100,000 parameters, but UNet has 1 million. So we're using only 0.3% of the parameters in this case. We can also look at the error versus the training size. So for the same number of samples in the training data, the PSNR from the DiffNet is much larger than with UNet, although eventually they're converging to similar values in the limit of very large trees. Similarly, in the inverse problem with no noise, we constantly have a higher PSNR, especially in the case where we have low numbers of samples, which is one of the advantages. In the inverse problem with different levels of noise, we're seeing, okay, consistent effects, but here the convergence comes earlier on, and with the higher noise, the similarity in the performance becomes more apparent with less number of samples. Another aspect is that we have an interpretable way of understanding the regularization. So by having this explicit form of this W, we can decompose into the differential part and the regularization part. So the regularization here just consists of a Tikhonov variable, because it's just on the diagonals of the, or let's say we're interpreting it in terms of the difference from the zero mean. Of course, in practice, you're learning some of the off-diagonal components so that they can also be have spatially varying regularization. But what we would expect is that the difference from the zero mean increases with the level of noise. So we estimate this by taking explicitly some of the off-diagonals minus the diagonal and taking the norm of this. And we do indeed find that this the magnitude of that regularizer, which has been learned together with the operator, is increasing with the noise level in approximately quadratic form, which we would expect with an L2 loss. So I guess one of the points I'm saying is that we have some greater interpretability about what the inversion operator is doing in terms of the components of an non-stationary diffusion process and a regularization process. Okay, so we also looked at the idea of looking at experimental data. So this is a experiment. So these are a little bit preliminary results performed by Giuseppe in conjunction with Charles Bell House at UCL, which is a biomedical research center. They have a number of physical funnels actually designed for ultrasound imaging, but they produce materials which have this kind of scattering density, which is spatially varying. So it's not easy to quantify that, but it is relatively easy to control the average scattering and some spatially varying aspects like the minimum and the maximum scattering and this spatial variation, spatial frequency variation. The idea was we produced a number of these samples, and the experiment is very simple. It's just put down on top of a tablet, and then we can put images through this and observe them with a camera. So I'll just show you one or two aspects. So here is this is experimental training. So this is one form of this, which is diffused, and you can see here. So this is putting this EMNIS database through, and you can see that we're getting quite noticeable spatially varying diffusion. When we run the inverse process with DiffNet, we're getting qualitatively good recovery. UNet is also performing, but appears a bit more blurred. And this, which is called interpretable DiffNet, is the version with the mean free operator number without the regularization added. So this is produced, you can start to see the noise accumulating or appearing in this inversion process. Then just some more examples. So in these examples, the average spatial diffusivity is varying over the image. So is increasing. This one is relatively weak scattering, although you can still see spatial variation. So both DiffNet and UNet are performing pretty well. UNet are performing pretty well. I'm increasing the blurring, increasing more. So this has probably pushed it beyond the limit of what it can achieve. If you look here, though, this is still doing recognizable deconvolution, and somewhat better, I would say, than UNet. Although it is, I mean, it's very difficult, I think, to perform completely fair comparisons. But one thing we can say is that UNet, with many more parameters, requires a much larger training set. Now, I want to just move on time to some generalizations of this to other PDs on specifically other image flows. So just going back to this stationary convolution problem again, we already wrote this. And let's write the kernel of the convolution in terms of canonical function and the scaling, representing the spatial width of the filter in a general way. So again, for the spatial convolution, stationary convolution, we have the Fourier transform result, product of Fourier transform of the field and the kernel. And then our hypothesis is that we will decompose this into concatenation of this canonical feature of this canonical kernel n times. So that implies that the scale operator h hat sigma is just the power n of the canonical. Now, if we now look at the Fourier transform, if we look at a Taylor series for the canonical function, we can write it in terms of derivatives of the Fourier domain in the normal way, and multiplied with powers of the spatial wave number k. And we'll just use this notation to represent the m-dimensional version of the wave number. So now this, moving back to the spatial domain, that means that we could represent this incremental convolution in terms of a magnitude operator, an advection term, a second order term, and so on, where these are the coefficients. So in the DiffNet that we showed previously, we were only learning this term. But now maybe we can generalize it to learn other terms. And this gamma is now formally will be dependent. In the stationary case, we could work this out explicitly in terms of the moments of the Fourier transform of the kernel. But now let's think of it in terms of a network. So let's consider a filter operator which produces this jet of derivatives in all its multinomial factors. And now we consider a learned operator for associated with each of these operators. So we could come up with this generalization which says that the incremental step is a time step times a set of weightings for each of these. And the summation of that over all of those variables will be the incremental step. So in terms of a network, this would look a bit like this. But each layer we would take f, we would take an explicit derivative to derive the derivatives up to chosen order. And then we would learn this multiplication, these multipliers and multiply them together. And then in this dotted line, well, we could consider whether this learned operator is learning from the image itself or whether it's learning from the derivative. This might provide a faster training. I'm not quite sure yet. So we'll call this a d lambda block of a So if we truncated this at J2, then it would be very similar to DiffNet with the addition of this advection. We'd be learning these coefficients plus these coefficients. And if, again, whatever order we truncated that, we would be enforcing a minimum number of vanishing moments. So now, again, we would then just conjecture that the inverse process could be replaced by learning a different set of coefficients, which were still dependent on the same derivatives of the image, but in the reverse direction. So again, for the stopping at order 2, we'd be learning these coefficients where now we've changed the sign of the advection. All right, so this was the idea for and he did a number of architectures which encode this idea, which we take the original image, producing the jet derivatives, and then learning these coefficients to add it to the generalized form. And this turns out to be similar to some other kernel estimations for variable convolution in some papers on image processing. Also, we considered how to achieve a multi-scale aspect by, as well as producing the image derivatives, producing the downsampled versions, learning the coefficients at each of those downscales and adding them back into the diffusion process. So 2 examples of trying to use that. And then if we look at image warping, we can represent it as just a transportation for a known displacement field F. So here's an example of a spatially varying warp cameraman. And we also, well, out of interest, I wanted to apply this to something more nonlinear. So this affine shortening flow, which is the rate of change in images proportional to the cube root of the curvature multiplied by the gradient of the image, which has this expression here. This is another kind of image enhancement process which looks to flatten the level sets of the image. So we produce training data of that. So here's an example for the affine shortening flow. So what we're trying to do, so this is the ground truth, and this is the affine shortening flow of that ground truth, and we're trying to learn these inversions steps. So here is UNet's version of it. Here is the previous DiffNet, gradient DiffNet, and multi-scale DiffNet. So these cases it's not so easy to see qualitatively which may be better. More so we look at quantitative results at the moment. Here's the warping example, and here we can see some more clear differences. So here's this input is the warped image, warped and slightly diffused version of the ground truth. So UNet is surprisingly, as often the case, doing fairly well. DiffNet also does fairly well. And here the multi-scale DiffNet is really showing quite some improvement. And quantitatively, we find that that's the case. So for the warping result, yeah, the multi-scale DiffNet outperforms also for the pronomalic, not for the affine shortening flow. And surprisingly, for the affine shortening flow, the original DiffNet. So this is a not this is a little bit of a puzzle at the moment, because this original DiffNet only has the second order derivatives and doesn't include anything which can represent the powers of those, so I'm not really sure how that works. Okay, so to summarize, the idea is that we're taking physics into account to obtain more expressive network architectures, which allows us to constrain operators based on our knowledge of the processes we're trying to emulate. One thing we definitely observe is that we have a reduction in the number of parameters required, which allows us to have an increased interpretability. There's a lot of aspects we still need to understand. We need to analyze stability estimates, and the regularization schemes are still somewhat simplistic because they're just relying on the regularization being learned through this already present structure. Whereas, of course, we could add some other regularization scheme at the end of the process. For example, a learn regularizer, denoising regularizer. But again, this would detract from interpretability. Should also mention that the idea of having spatial variation network is also not new. It relates to lots of work done on attention layers, which essentially provides a multiplicative weighting to the learned network. But we started working on that. I haven't got any. I want to look at other flows that we can write down in terms of image operations, image-based PDEs, and eventually to look into dimensions higher than 2. And another possibility will be to, because this multi-scale aspect seems to be quite powerful, make a connection to the use of the wavelets approach. Wavelet schemes obviously don't have an explicit interpretation in terms of spatial derivatives, but they qualitatively bear a relationship. Okay, and so I think I'll stop there. At the end, and if there's any questions, I'll be happy to take.
So I'll kick off, Simon. Just all of your.
All right, go on.
Sorry?
Yes, that's fine. Yes, go ahead.
All of your problems have worked with second order operators, and you've got maximum principles and stuff floating around to help you. Can you extend this to the fourth order operators you use in image processing?
Well, they weren't entirely there. I mean, we also had the warping, which was first order. But yeah, there's no reason why that shouldn't be done. I mean, the gradient diff net does include operators up to any chosen order.
Okay.
But we didn't test it on any explicit higher order data. But I think there's no reason. I mean, there's no, we're not relying on the maximum principle anymore.
Okay.
Thank you. Yeah. Yeah. Well, that's of course true, but we can't estimate that very easily. But for the diagram, we can explicitly get it from the deviation from Jeremy. I don't know. I mean, I was thinking the same thing. There could be some effect. I mean, almost certainly there is. Yeah. But then it's an interpretation. Are you learning? Are you interpreting that as learning the components of that derivative operator, or are you learning? I don't see a way to start that. But at least from what we saw in the result, there is a clear relationship between the diagonal the deviation from the mean on the diagonal and the noise level, which is something that's not expected. Yeah. Oh, Chris couldn't hear the question. Oh, sorry. I don't know. I don't quite understand. I guess we're using this mic. Yeah. Yeah. So maybe you need to. Yeah. 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 Oh, right. So the question is it possible? That is possible. I mean, there is practical math which does do that. Obviously, implementation of that is quite tricky because you have to include memory effect over time. You can't just do it as layers. You could do it in the Fourier domain, of course, but that. Okay. How do we know this? Yeah, the question was about fractal derivatives. And yeah, I mean, there are fractal networks. I mean, that's definitely would be interesting, particularly because the A5 shortening flow or other of these curvature flows technically use powers of the derivatives. So when we applied it, I mean, we weren't exactly expecting to see that it would work, but it's an interesting question that people address at these low PDs. And in general, you observe some physical problem and you want to learn a PD. Can it be expressed in terms of integer powers of derivative operators or in terms of fractional powers? I guess it's not known, but I mean, it's a relevant question to ask. I mean, I would like to extend it to that. I'm not sure the best way to do it.
So when you use it for deconvolution, can you visualize the convolutional curves that you learned?
Yes, we did. I mean, I didn't include that here. But yeah, we can do that. And then generally speaking, I mean, you'll find that the higher frequencies are appearing later in the network. I mean, yeah, I think those are in the paper. But again, explicitly interpreting them, I'm not quite sure. I mean, but probably the thing would be to design more carefully some phantom units, test cases where we can predict what we would expect to see. Yeah. Yes. I haven't really thought about that. You were saying it's non-Markov. Oh, sorry. Because of the skip connections, yeah. So the question was about the fact that UNet is non-Markovian because of the skip connection. But on the other hand, I mean, I interpret DiffNet. I mean, all of the scales in DiffNet are used. I mean, it's not really interpreted in terms of time evolution, right? But if you were putting a UNet incrementally in time, it would still be first order, so it would be Markovian in that sense. Obviously, some work has been done on higher order schemes in time. Both and Haver have what's it called, HyperNet, which is second order in time, and you may be hearing about that later today. So basically, I think many of us at this program are interested in this whole connection between PDs and networks. So when you write down the discrimination of PD and implement it, and then you layer architecture. It's just often just language interpretation. Right? There's several other things like REST. This is well known, right? Spoilers from PDE, except that, or some ODE even, except that it's not explicit what that is. Now, if you, so all we're basically doing here, if you're restricting our kernels to be explicitly derivative operators, then we have a more direct interpretability. But of course, we're not do that. But maybe applying it to this. Okay.
I think we're saturating here for now. Are there more questions from the remote participants? So by the way, we are going to go now into the coffee area of the INI and have coffee. So I'm going to take my phone with me, and so I can take you with me as well to the coffee area. We did that also last week, so we are going to communicate with you over the phone if you wanted to stay on and have a chat. You can take us anywhere.
But I should log out.
Yes, I will.
I'll log out of
Yes,
this. Maybe they stop the. Maybe they stop the recording. Okay. Thank you, everyone. I'm going to check out, but apparently we can stay in. So
Great stuff, Simon. Thank you.
great. Maybe see you later.